Now that we're done with goal and scope definition of an LCA, we move on to lifecycle inventory analysis, or LCI. LCI is the phase of an LCA that involves the compilation and quantification of inputs and outputs for a product throughout its lifecycle. Inputs and outputs are product, material, or energy flows that enter or leave a unit process. And a unit process is the smallest element considered in the lifecycle inventory analysis for which input and output data are quantified. We will be more familiar with these terms as and when we go more into this lecture. So an example here is a set of unit processes within a small product system. So on the left you can see various inputs that are flowing into these three unit processes, and each of these unit processes have an output, and some of them also have input from other unit processes. These are also called intermediate flows. And looking at a more broader picture, you can have your entire product system with various different input or unit processes that combine into transport, also raw material acquisition, energy supply, waste treatment, recycling, and also external factors such as having some product flow from other systems, elementary flows, and also what happens when your product is done. So where does your elementary flow go outside of your system and also to other systems? So now we're going to talk about some of the key stages within lifecycle inventory analysis. So the first key stage is preparing for your data collection. So on the right hand side you see this table with many fields that is something called as a collection table. So you can see these fields like material inputs, energy consumption, energy inputs, and also water consumption. For each of them you have some kind of units and also the quantity that is being analyzed. And you also simultaneously keep a record of the methodology you're using to collect this data in the first place, and also the origin of where this data is coming from and also where your flow is coming from. Similarly, you also have your material output, so everything that is coming out of this unit process. And similarly, you have its units, quantity, the description of how you're collecting this data, and also where the destination of this material output. The next important stage, once you have done your data collection, is for validation. So once you have your data, it must be validated to confirm and provide evidence for the data quality requirements that you defined in the beginning, both during and after the process of data collection. This can also involve establishing mass and energy balances. So sometimes it's very important and very easy to see that, okay, 10 kilograms of water was going into a system, but somehow only 9 kilograms is coming out of it. So it probably makes sense to make sure, okay, where did that extra 1 kilogram go? So obvious anomalies like this can necessitate collecting alternative data or maybe changing the methodology in which you're collecting your data. So once you have a solid amount of data, it's now time to relate your unit process and functional unit with this data. So based on the flow chart between all the flows between your unit processes, and the flows of the unit processes are then related to the reference flow. This calculation should result in all the system input and output data being referenced to the functional unit. Essentially, if you can remember that the measure of the products or product parts required to deliver the performance defined by the functional unit is what you need here. So from the EU study, in the example of a truck, a very specific transport scenario would have to be defined in the study that uses the data set for the specific truck being used, that basically ensures that again you have like a clear identification and quantification of your data. For example, the transport scenario that they have of a 150 kilometer overland transport of bulk sand at about 90% load factor has the quantity and unit of 1 ton kilometer and has a very specific data set from which that data is coming from. So there's a very, very technical definition of relating your unit process and functional unit, so it's not very trivial. In the example of the MUSH-R project, we had an experimental estimation of our colonizable volume. So we made experiments and it turns out that a 5-liter substrate bag that was non-reusable essentially weighed 30 grams but had essentially the same volume as our reusable bags. And this is basically because you have to fold the bag a couple of times in order to seal it, so it loses some efficiency in volume there. And the colonizable volume of the 3-liter bucket is still 3 liters because there is no change. It's essentially space efficient. The only difference is that it essentially weighs 3 times as much, so 90 grams. This allows us to basically scale and compare the 2 different container types on very similar terms. So for example, if you have 100 grams of substrate bags, they can contain 1,000 times 3 divided by 30 liters of substrate, so essentially 100 liters of substrate. Similarly, you can compute that the same weight of substrate buckets will contain 33.333 liters of substrate, so it's 3 times less. Once you've related your data with your functional unit, we go into refining your system boundary. So the initial system boundary is basically revised, and this is done in accordance with the cutoff criteria that you established before. And when you do this analysis, it may result in exclusion of certain life cycle stages or unit processes if they lack significance. Sometimes what you do is you exclude certain inputs or outputs that are not relevant, and you might also include new unit processes, inputs or outputs that might be shown to be more significant than estimated before.